Hello and welcome back to Chapter 10, Carbohydrate Metabolism 2, Aerobic. So this is the big chapter where people like me are dreading, where it's just a ton of info and so dry. But you just have to get through it. Sorry Biochem majors, but this isn't for me. Anyway, let's get through it. As we may know, the pyruvate generated from glycolysis has to go somewhere, and mainly into the citric acid cycle. Before that, let's talk about how fatty acid, beta oxidation, amino acid catabolism, and alcohol can also come into play. Now, they, just like how pyruvate can be generated into acetyl-CoA through pyruvate dehydrogenase, these three fatty acid, beta oxidation can also make acetyl-CoA to feed into the cycle, and that's done through the carnitine transporter into the matrix. Fatty acid is usually generated outside from the cytoplasm, so it has to be brought in using the transporter. Amino acid, usually termed ketogenic, which is not glucogenic. Well, there are some that shares both, but ketogenic amino acids specifically, they lose their amino part and their carbon part forms the ketone bodies. So they also feed into the acetyl-CoA over here. And alcohol, surprise, they also create acetyl-CoA, but only a minuscule amount before the overload of NADH prevents it from generating any more. So they feed into acetyl-CoA here, and if we recall, pyruvate can be generated from both the glycolysis step as well as glucogenic amino acids, like alanine. Now, once using pyruvate dehydrogenase complex into acetyl-CoA, then we have the citric acid cycle, which is a series of steps to oxidize a huge compound and lose the 6 carbons eventually. So starting here, we use citrate synthase to generate citrate, and then use cis iconitase to generate isocitrate. And this is done through intermediates. And isocitrate turning into alpha ketoglutarate is the rate limiting step using isocitrate dehydrogenase. This is the first step where it generates NADH as well as the first carbon dioxide molecule, and that gets yoinked off, the first carbon that gets yoinked off. And then alpha ketoglutarate then uses alpha ketoglutarate dehydrogenase. You see the pattern here, dehydrogenase, right? To take away something. Dehydrogenase and turn into succinyl-CoA, and that forms the second NADH as well as the second carbon dioxide. And then succinyl-CoA then uses succinyl-CoA synthesase. Synthesase requires energy, but it also generates a molecule of GTP, which is, think of it as equivalent as ATP. Then it generates succinate, and the succinate goes ahead and turn into fumarate with the assistance of complex 2 on the inner membrane. And it generates FADH2, which also has reduction potential that can later be used and oxidized and used to pump protons into the electron transport chain. And this is using succinate dehydrogenase. Surprise, again, the same pattern, dehydrogenase. And then fumarate uses fumarase, turned into malate. And then malate then is turned back to oxaloacetate using malate dehydrogenase. And that generates our final NADH molecule. And then oxaloacetate combines with acetyl-CoA. This is a 4-carbon molecule. Acetyl-CoA is a 2-carbon molecule, and that combines together to form citrate again. Now, the 3 big steps to remember are the citrate synthase, the isocitrate dehydrogenase, as well as alpha ketoglutarate dehydrogenase. These 3 are like the big steps, mainly because they are regulated by negative feedback by NADH, ATP. Citrate, succinyl-CoA limits this. These 2 steps are limited by NADH and ATP mainly, as well as their products. Now, where do the NADH and FADH2 go? Well, in aerobic respiration, you use oxygen as a final electron acceptor. So what this do is it slowly reduces the potential a little bit, oxidizes it a little bit, and uses that energy to pump protons into the intermembrane space, which is between the inner membrane and the outer membrane of the mitochondria. So what this does is pump it into intermembrane space and then use a gradient to generate the ATP by feedback pump, like the backflow pump. So imagine you're just pumping water through a dam and then using all that water dam to power a water wheel all at once. So complex 1 is where NADH compounds go, and then their electrons generates 4 protons feeding to the intermembrane space. Complex 2 uses succinate and FAD, which this is existing on a complex 2, generates a FADH2, and that feeds 0 protons because the main thing this goes is just to further reduce the iron sulfate complex on the complex. So that coenzyme Q, the coenzyme Q travels from here to here, and then finally to complex 3, which it passes on the potential to cytochrome C, where it also pushes 4 protons into the intermembrane space. And then finally at complex 4, the cytochrome C then passes the final electrons to oxygen, where it's a final electron acceptor, and it generates water at the same time. And then creates 2 protons further into intermembrane space. And that totals protons goes ahead and pump back to generate ATP. Now there are some shuttles, NADH shuttles, because there are NADH from the glycolysis that we covered, right? Not only glycolysis, but also acetyl-CoA by pyruvate dehydrogenase. Well, this step already happened in the matrix, so it doesn't matter. But from the glycolysis step, we saw how G3P, glycerol 3-phosphate, which is the next step after DHAP, the generated NADH goes and has to be on the membrane, and that has a specific molecule that it goes ahead and gains electrons, so that's reduction. So it goes ahead and reduces the FAD into FADH2, so FADH2 then can go ahead and be oxidized here at complex 2 to generate 1.5 ATP, whereas NADH through the malate aspartate shuttle can directly be flown into and generate the NADH molecule, which generates a 2.5 ATP potential. So there's a difference in potential by the 2 different molecules, NADH versus FADH2. So if we do the math here, 1, 2, 3 NADH here, 1 ATP, and 1 FADH2, if each NADH generates 2.5, that is 7.5 in total, and if each is 1.5, so that's 8, 9, 9 and plus 1, that's 10 ATP, and that times 2, that's 20 total ATP just through this. We also have PDH, making that 1 NADH molecule here, so as well as the entire glycolysis step, making 1 NADH molecule, so that generates 2 NADH, and that multiplied by 2 because there's 2 of them, so that is 10 altogether, and then plus the 2 more ATP generated by glycolysis, so that's about 32 in total. But of course it would be less than that for across most tissues, because, well, there's the difference in the G3P shuttles, right? The NADH might not make it into, and it will actually turn into FADH2 due to the G3P shuttle being placed. Now, how does the chemiosmotic coupling work? Well, in the ATP synthase shuttle, it uses the F0 subunit as well as F1 subunit. It looks like a trigonal thing. So it's like a 3-way triangle thing, and the F0 subunit is where the protons actually go in through the channel, and the F1 subunit, the 3 parts, is where ADP actually turns to ATP. So that's pretty much it. Lots of info. Final thing is ADP and oxygen O2 are like the rate limiters for the entire thing. So be sure to know which ones are inhibiting and which ones are feeding forward.